Alright, so let's start looking at some more complicated circuits. Here is a multi-loop circuit, although still simple in the sense that we can reduce it to equivalent resistors. So label the current through each resistor, including its direction and size. One approach would be to reduce the circuit to its equivalent resistance, which in this case will work. Sometimes it doesn't. Here I do this kind of thing. This is how I tend to do it. I take the circuit and I replace the innermost kind of thing. In other words, the thing that can be done, these are in parallel. I can't reduce, say, this with this because it's neither in series nor in parallel. It's kind of in series, but the ends are not, right? But there's an option for current can come in and out, and it's not really in parallel because the endpoints are not connected to the same place. So that's not so good. But here, they are an actual parallel resistance, so I can convert them into an equivalent resistance. It turns out that with a 600 and a 400, I get 240 out as their equivalent resistance, which makes me happy in that it's less than either of them, which we know has to be true for parallel circuits. Now we have these two, and they are in pure series, so we can replace them with something which is this, their sum. The sum, of course, of 240 and 560 happens to be 800. Isn't that convenient? And then we can replace both of these guys with a 400 ohm resistor because they're in parallel, and two equal resistors in parallel have an equivalent resistance which is half as large. That just follows from the formula. It's not something to memorize, but there you go. So we know that our battery sees a resistance of 400 and a load of 400 ohms, which means that the current is 0.030 amps, right? 12 volts over 400. Of course, going back to this one, that current then splits down two symmetric branches, so the current through here has to be half as much, and the current through here has to be half as much, which means through our 800 ohm resistor, we get 0.015 amps. The current through the 560 ohm resistor is the same as the current down the right branch. That is also 0.015. Once we know that, we can say that that means the resistor has a potential difference of what turns out to be 8.4 volts. But the potential difference across the entire branch it's in is 12 volts. So the potential across the two parallel guys must be 3.6 volts. And that's true for both R2 and R3, the 600 and 400. And so once we know the potential difference across, say, the 600, we can figure out its current by taking 3.6 and divide by 600, getting 0.006. Or take 3.6 divided by 400 and get 0.009. And notice that these two actually do add up to the 0.015 that we needed. So everything is self-consistent, which is nice. All right. Grounding. Circuit analysis depends only on potential differences, not the absolute potential, which after all doesn't really exist. And this can complicate things if different circuits are brought into contact, so it's best if they have a common reference potential. Also, it's also good that you could theoretically, in a free-floating circuit, you could have voltages get very large, and if someone then crosses into that circuit, they could become a path of least resistance for the circuit to discharge into the ground. So you'd rather not do that by having the circuit already grounded. We achieve this by running a wire from each of the circuits we have into the ground and choosing the earth to be at 0 volts. This gives all circuits the same 0 point. Notice that the wire in these cases is singular. There's no wire running. There's no closed loop. No wire runs back, and so no current flows in it. The circuit behaves just as it had before. So here we have a grounded circuit. How do we know? Because we've got this special symbol here, the kind of arrow of progressively small leads. I don't really know the history as to why that's the grounding circuit, although I suspect it's meant to evoke the idea that you're taking something with a tip and jamming it into the earth. That forces this to be at 0 volts, which means all on the line with it, there's 0 volts. And then we can figure everything out. So we say, well, we've got a 10 volt source, so it's going to make this point 10 volts higher than that point. And this is the same as this because there's been no place to dissipate. And then we're saying the way this, with the particular current we have, that this drops 4 volts and then drops another 6 volts. And we're back to the 0 and back out. So, well, I guess not back out. I think it goes out here. But the circuit can flow this way, and any excess charge would flow in or out of the circuit if we needed it. What would happen if we instead grounded it here? So we broke this grounding pin and we put that grounding pin. Not much really changes, but now we of course see that we lose 6 volts going here, so it's minus 6 volts. We gain 10, so we've picked up to 4. we go over to 4 as before, and then we lose the 4 that we had up here back to the ground. So everything looks the same, but now we're grounding out to this place. All right, we're calling that 0 volts. And in general, that's all we really need to worry about. All right, now set up the equations you could use to find the current through each resistor. Here, life is more complicated than before, so you can't just get equivalent resistances. Why not? Because this ability to split means that R1 is not in series with R5 since there's an option to go this way instead, and it's not in parallel with R5 because its endpoints are not connected to the same as that. These 2 points are different. As a hint, that means you're going to have to use Kirchhoff's rules. I chose set up this way, where I've made a bunch of loops. I took this loop and called it A. So I start down here, and I gain the EMF of the battery, and then I'm moving the correct way with I1 through the resistance R1, so it loses potential I1 R1, and likewise I'm going the same direction through here, the correct direction. Here's my arrow, and so I get minus I3 R3 like this. Same sort of thing when I take loop B, which is this outer loop here, and goes through these guys. Everybody's going the right direction, quote unquote right direction. I'm traversing the path along my currents that I've drawn, and so I again get the EMF minus I2 R2 minus I4 R4. That gets more interesting if I go into loop C. So loop C, I'm going to start down here and go like this, going clockwise around the loop, but notice that that direction is opposite to the direction I said the current is going, so I know that this has to be a lower potential than this, so I need to gain I1 R1 in potential this way. I go over here, oh look, I'm flowing with the current the correct direction, it's going downward, I'm going downward, so this is a drop, so I get minus I2 R2, and then again, for this one I'm going against the current, and so I get plus I5 R5. And likewise for loop D. In addition to all of those, and there are some other loops that I didn't bother drawing, but in addition to all of those, we have the 2 junction rules, which is that current flowing into here, I1 splits into either being I3 or I5. And then current flowing here is either I5 or I2, and they join to become I4. So that's what those express. I have 5 unknowns, the 5 currents. I have here at least 6 equations, so I can pick any of the things I want. In general, it will be nice to use the junction rules, and then whatever's left you fill in with your voltage loops, although it really is up to you, and whatever occurs to you to solve it is the way to go. Here I've taken the first 3 loops I had drawn, A, B, and C, and then the 2 junctions. I also set up in this weird matrix form, which is not necessary, but it's a way to solve the system of 5 equations and 5 unknowns. Solve that system any way you want. It's a linear system, so it'll be relatively straightforward to solve, and there are many methods. I honestly just threw it online. I went here and I went to this website and said, hey, it said fill in your matrix and fill in the other bits of the matrix, like the constants, and spit out this answer, which certainly seems reasonable. At least it has the right symmetries.